Okay, so I just want to go over the answer key in case we don't have time to go over this homework assignment in class. So the first page, it's all 1D motion problems. Before I give you the answers, I just want to go over the general procedure of how you should be solving these problems. So first off, we read through the problem, right? So they have a skier starting from rest. I circled from rest because that tells us something. It's the initial velocity of the skier. So I write that down. VI equals 0 meters per second. I keep reading. They ski straight down a slope 100 meters long. So I saw that that was a variable. I underlined it, and I wrote down what it is over here. This is our distance. It is 100 meters in 8 seconds. So again, I saw that was a variable. So I said the time equals 8 seconds. What is the magnitude of the acceleration of the skier? So again, I highlight this thing, acceleration, and I write down, this is what we're trying to find out, right? A equals question mark. So then I take these variables and I say, okay, what equation in my reference tables has these variables? I go to my reference tables and this is the equation I found. I substitute in my variables with units, right? I have 100 meters here. VI is 0 meters per second, so that just kind of goes away. And then I have 1/2 a t squared. And then all you have to do at that point is use algebra to solve for a. So, what's really important to remember here is it says, show all work, including the equation and substitution with units. So, you need to have your equation, that's one point, your substitution with units, that's another point, and your answer. So for this one, I got 3.1 meters per second squared. For 2, I got 2.5 meters per second squared. For 3, I got 7.14 meters per second. And for A, I got -4 meters per second squared. So here you can see each equation I used, here, here, and here. But I had the same procedure for each one, which was writing down the variables in the problem, right? Both the given ones right here and the non-given one, like the one they want us to find. This is your wanted variable. These are your given variables. Then I picked my equation. Then I substituted in my variables with units here, always including the unit for each one, and I found my answer. Okay? And that would give me 1 point, 2 point, 3 points for each one of these. Okay? This one's a little tricky. This line over the V means average velocity. And if you go to your reference tables, they define each variable, and they'll write V with a line over is average velocity or average speed. And here I ask for the average speed. On the second page, they give us this velocity time graph. They say it represents the motion of a car during some 8-second time interval. The first thing they ask for is the displacement of the car. So always remember that the displacement, I'll just write disp for displacement, is the area under your velocity versus time graph. So we need to find the area under this graph. It's pretty simple for this graph. It isn't super complicated. The first thing we need to do is just highlight that area. I'll shade it in. It's just the space between this graph here and the axes. I can split it up into 2 easy to find shapes. So this is a triangle right here, right there, there's a triangle, and this is a rectangle. So I can't really find the area of this whole thing, but I can find the area of this part and the area of this part, and if I add those areas, I get the total displacement. So to find the area of the triangle is just area equals 1/2 base times height. To find the area of the rectangle, it's just going to be area equals length times width. In the case of the triangle, the base is 4 seconds, the height is 6 meters per second. In the case of the rectangle, the length is going to be 4 seconds, and the width is going to be 6 meters per second. If you calculate these areas, you should get 24 meters for the triangle. No. Remember, you have to divide by 2, right? It's 1/2 base times height, so it's going to be 12 meters for the triangle, and you're going to get 24 meters for the rectangle. and you can work out the math yourself. In this problem, I'm not asking you to show your work, so it'll only be worth 1 point. Your total your answer is just going to be the sum of these two areas, which is going to be 36 meters. We added up in total. But you can work that out on your own. Just find the area of this triangle, find the area of this rectangle, and add the two together to get the total displacement. In problem 6, we need to find the acceleration of the car at t equals 2 seconds. So we need the acceleration at this point right here. Okay? We can see in this whole segment right here, we kind of have like a straight line, right? So the slope is going to be the same here, here, here. It's going to be the same during this whole segment. And the slope of this graph is the acceleration of the object. So the slope of your velocity versus time graph is acceleration. So all you need to do is pick 2 points near t equals 2 seconds, right? 1 point before, 1 point after, and then find the slope between those 2 points. So the points that I picked were right here at, v equals 0 meters per second and t equals 0 seconds, and right here at t equals 4 seconds. You can pull this line up there. Slope is going to be rise over run, so we're using this formula. Slope is delta y over delta x. So we need to find out what our x values and y values are. In the case of our first point, we're going to have y1 be 0 meters per second, x1 is 0 meters per second. By x1, y1, I mean this equation expands to y2 minus y1 over x2 minus x1. Here, y2 would be 6 meters per second, x2 would be 4 seconds. So I plug in those numbers. This is going to equal 6 meters per second minus 0 meters per second over 4 seconds minus 0 seconds. So all I'm doing here is finding the slope in this part of the graph, and that's going to be the same thing as the slope in this part right here at t equals 2 seconds. I have the straight line. The slope is the same everywhere. You should get 1.5 meters per second squared. But again, I didn't ask you to show your work. I didn't write that phrase, show all work, including the equation with substitution, blah, 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 blah. I just asked for an answer. You get full credit as long as you just write what your answer is going to be. You don't need to show your work. On the last page of this homework assignment, I'm asking you to match these graphs with these descriptions. So the answers are graph 2, graph 4, graph 1, graph 6, graph 3, and then graph 5 in that order. I can go through each one for you right now. So for example, if I look at this one first, I'm just going to describe the graph. I see an object that has constant speed or constant velocity. How do I know that? The position is increasing at the same rate in the same amount of time. So it is constant speed, constant velocity. You can think the slope of this graph isn't changing at each point, right? It's going to be some value here, the same value over here, the same value here. So my velocity is constant. My velocity is also positive. I know it's positive because my position is increasing, okay? And velocity is position over time, or change in position over time. If my position is increasing, my velocity is positive. So I know I have a positive velocity because my position is increasing, and no acceleration. So I go over here, which of these is that? That's going to be this one, right? Positive constant velocity, parentheses, 0 acceleration. I keep going. So 2, for example. Again, positive velocity. Why positive velocity? Because my position is increasing. What about the acceleration? We need to look at what's happening to the slope. So here you can see in the beginning the slope's very, very high, right? It's steep. And then it's not as steep. So I can say the velocity is decreasing. And if the velocity is decreasing, I have negative acceleration. So I have something with positive velocity, negative acceleration. That's that description. Keep on going. This one has negative velocity because my position is decreasing. However, again, there's no acceleration because my velocity is not changing. So I need something with negative velocity and 0 acceleration. That's this description. Keep going. We have something where our position is increasing in 4. If our position is increasing, we have positive velocity, but the slope of this graph is also increasing, right? The slope is the velocity is increasing, that means we have positive acceleration. So that's going to have, we need something with positive velocity, positive acceleration. That's this description right here. Keep going. This is an object that's not moving at all. It has 0 velocity, 0 acceleration, right? That's something that's not moving. It's at rest, we call it. At rest means not moving. That's this description right here. This one, again, velocity is negative because the position is decreasing. If we look at the slope, here the slope is about 0. Here the slope is negative, right? Again, the slope is velocity, the slope of this position time graph. So we can say that since the velocity is decreasing, we have negative acceleration. So we have an object with negative velocity and negative acceleration. That's this description. So all I'm doing in this case is figuring out, okay, is the velocity positive or negative? Is the acceleration positive or negative? I can infer that all from the graph. You can remember the smiley face rule, right? If we look at our position time graph, if it kind of curves up, so it could look like this, curving up, or like this, curving up, it has positive acceleration. So this problem has positive acceleration, right? It's curving upwards. The slope is increasing, okay? And then we have our frowny face here. So this one was positive acceleration. This one's going to be negative acceleration because the slope is decreasing, right? Here it's steep and positive. Then it's kind of gradual but still positive. Here it's kind of 0. Then it's sort of negative. Then it's really steep and negative. So it's decreasing velocity. It's negative acceleration, and that's the case of 6. That one has negative acceleration. It's a frowny face, kind of like half of a frowny face. 2 also, it's like the other half of that frowny face. So I can say that 2 and 6 are like frowny faces. Those are negative acceleration. This one's a happy face. That's positive acceleration, right? What would be the other graph of this? The other happy face graph would be like this. Position, time. It's curving up. It has positive acceleration. Think, here the velocity is negative and steep. Here it's kind of 0. My velocity increased. I accelerated. I had a positive acceleration. In each of these cases, I'm not accelerating because my velocity is the same. Here my velocity is positive and the same. Here my velocity is negative and the same. Here my velocity is 0 and not changing. In this number 8, that's hard. I'll admit that problem is hard. I kind of offered it as extra practice. It's not really needed that you're able to do this, okay? But if you can do it, that's fantastic. You're doing great. Just go by these descriptions and try and draw a graph of what's happening. So, for example, for the first one, I have something that, here, look at my description for 1, something that has a positive constant velocity. So I drew a graph of positive velocity that isn't changing. It's constant positive velocity. For 2, my description was positive velocity but negative acceleration. So the velocity has to be positive, but it has to be decreasing. And keep going, drawing your graphs for each one. But again, this is more like you're going above and beyond. You're really doing a great job if you're even able to try this stuff. This is more of like the important stuff, looking at these position time graphs, relating that to velocity and acceleration. This is like the fundamental stuff. This is the more, you're doing awesome stuff.